Dr. N. Kasthuri, working as a professor in Department of ECE. In today's class, I am going to handle about the electromagnetic field. In electromagnetic field theory, the two things which are very important. One is electric field. Another thing is magnetic field. In this class, we will discuss about the electric fields. So in today's class, let us see the boundary conditions of electrical field. If you look at the conditions and the interface of any media, this is we are going to discuss on boundary conditions of electrical field. Electric field. So why we need to analyze is, if there is any interface between any electrical field, the conditions of the electrical field is getting varied. So the conditions of these electrical field at the interface, we are calling it as an boundary conditions. So if you look at these boundary conditions, there are the boundary conditions can be analyzed for various kind of interfaces. One thing is, the medium may be a dielectric. So one media is a one dielectric, another media is another dielectric. So we need to go through the conditions, boundary conditions for dielectric interface. That is first, in dielectric interface. Then maybe it is an dielectric conductor interface. Dielectric conductor interface. Then this is one second interface. The third interface is that is conductor interface. Conductor interface. Then it becomes maybe a dielectric and air interface. Media is air, dielectric air interface. So in this class, let us go through the dielectric interface. So before that, what we need to understand is, so how the electric field will, the behavior of the electric field is getting changed, that we need to analyze. So if you talk about electric field, so the electric field E depends on, right? Maybe I can say that the electric field vector is proportional to Q. That proportionality constant, I can replace it as KQ divided by R square. So this K, we actually in general, K has been denoted as 1 by 4 pi. So therefore we can say that Q divided by 4 pi R square. So if you look at the electric field, so meaning, what is the meaning of this relationship, right? So suppose I have a charge here, right? Then if the distance, suppose if I am analyzing the field at this distance, suppose I am analyzing the field at this distance, so analyzing this field at this distance. So if the distance, this is my distance R. So as R is getting increases, when R increases, definitely the electric field is getting decreases. So this electric field is getting decreases. Suppose assuming that I have an electric field. So this is my field line. This is my field lines. So I am telling you that what is the need for analyzing the boundary conditions, right? So in this electric field, if you look at, I have a surface, right? Here I'll be having some media. So that is a surface is here, right? So now what I'm doing is, as we know, E is inversely proportional to R. So meaning that I'm taking electric field at y-axis and distance, that is radius in x-axis. So in general, what you will say is, depending upon the distance R, the electric field potential is gradually getting decreases. So what happens is, at the that is at in between this field, I am keeping this surface, right? Some materials I am placing. So what will happens is, this since because of this, the electric field maybe, right, this is the electric field from this surface, the electric field direction may be like this, and maybe this, right, either this way or this way. Suppose if you talk about, right, the field towards this direction. So in this side, at the interface side, right, at the interface side, there is, since because, right, this that is, this is opposite in front, this side, since this direction of this, the force created by this object, right, is generating this electrical field, so the net electrical field will get decreases. But here the field direction, the field due to this object is also same direction. So this, in this space, the field potential get increases. Here the field potential get decreases, here the field potential get increases. So thereby what will happen is, at this interface side, right, at this interface there is a chance for, so at this interface here, the field potential is getting decreases, and this, in general graph is this, general graph is this, right, this is a general graph. There, if there is no media, if there is some any interface, I mean object, what it does is, this this electric field intensity is getting decreases at the intersection of the boundary, right, that is a boundary, this is a surface boundary. What will happens is, this side, right, why I am reducing this magnetic strength, right, this is original field, now this is a reduced electrical field strength, since because of this opposite direction, the electric field get decreases at this intersection, right. Now since because of this adding of this electrical field, the field get increases, and then again because of the radius it gets decreases, right. So at this interface, this is called as an interface, right. So at this interface we need to analyze how the electric field behavior is changing. That is why we need to study about the boundary conditions of the electrical field. So let me give the boundary conditions, right. The boundary conditions can be done for two different things, right. That is, one thing is, what I can do is, I can take, right, let us consider, I can consider the surface like this, right. This is my surface. So this is my surface boundary interface between the two fields. So at one side I have an dielectric, because I am talking about dielectric interface. So here I have one dielectric that is having a refractive index epsilon r1. So the sorry, it's not refractive index, it is permittivity of, this is epsilon r1, this is epsilon r2, right. This is a medium 1, this is medium 1, this is medium 2, this is medium 2. So this is media 1, media 2, which is having permittivity, that is this is called as an okay, epsilon r1 and epsilon r2. This is permittivity, right. Permittivity is epsilon r1, epsilon r2. Now if you look at the electric field, right, see, generally any field will contain two components, right. This, if I am talking about E component, E may have E tangential plus E normal, right. So electric field means it will contain tangential as well as normal. So the tangential component, right, this is, now I am going to mark this field here, right. So that is, if I am talking about, this is my field, right, this is my E tangential, right? Maybe this is T2, because this is medium 2, and this is my normal component, right, this is my normal component, this is called as an En1. This is normal is denoted as N, tangential is denoted as T, media is denoted as depending upon the medium, this is also 2, right. This is Et2, En2, this will create a general electric field, this is E2. Similarly, I can also draw for this. So there, this component, right, this component is, now this is my electric field E1. So this will contain, right, this will contain an tangential component, right? This is my tangential component, this is Et1, and this is En1, right, this is En1. So this is En1. This will create an electric field E1. So now what does this boundary condition helps us is, this will help us to find out, right, how, if suppose, if I know E2, if E2, that is electrical field strength in medium 2 is known, I can able to find out when it crosses the interface, how does it gets affected in E1, I can able to calculate. That is why this boundary condition will be useful. Suppose when you want to analyze this, the first thing is, I need to put, right, this is can be analyzed by using two ways. One thing is, first one I can do it by closed loop, right, closed loop analysis. This is, I'll take a closed loop, right. So in this case, this is, let me put it as A, B, C and D. So what I'm going to find out is, in this closed loop, I am going to find out what is the overall electrical field. So when I am making this integration, right, integration of E, right, that is electrical field dot dl vector, right. This is my, according to your Gauss law, right. This is your this EDL, right, is equal to 0, right. So now what I need to do is, this will consisting of 4 different. Now let me check this as this with this delta W, right, this with this delta W, and this I'll take it as delta H. Height is delta H, again this is also delta W. Now what I need to do is, I need to put this is whole integral, no, this is the overall this entire path. So therefore I can put it as, this will indicates integration of A to B into E versus dl. Similarly B to C, E versus dl, E dot dl, and then C to D, E dot dl, and similarly plus this again D to A. This is D to A, E versus E dot dl, right. The overall thing is equal to 0. Now what I need to find out from A to B, if I am looking at, this is nothing but ET1, right. ET1 is here, ET1. So therefore this indicates that integration of, this is sorry, not integration, ET1. ET1 into delta W, right. This is first thing, ET1 into delta W. This direction is also same, right. Therefore I put it as positive. From B to C, if you look at, from B to this interface, right, this is junction, at this junction. So I can put it as, from B to this junction, what is the component? The component is normal. So this direction I'll mark it like this. So this normal component is, this normal component and this normal component are opposite. So therefore I can put this as plus E, this is N1. So therefore this is direction is opposite. So therefore I put it as minus. This is minus En1 into delta H by 2, because it is half only, right. Again in the bottom portion, from this junction to C, again this direction, these directions are opposite, right. En2 and these directions are opposite. So therefore minus En2, right. This is N2 into del H by 2, right. Then from C to D, again this tangential and this tangential, right. This tangential, this I need to mark it like this. This is tangential ET1. This also in this same direction, right. This is ET2. So this ET2 and these directions are opposite. So therefore I can put it as minus ET2 into delta W. Again from this D to this junction, right. From this D to this junction, this vector are both are same direction. So I can put it as plus En2, correct, En2 into delta H by 2. And similarly from junction to A, it becomes, this direction is also very similar to En1, right. Direction, you need to note down the both the directions, right. So this direction, these directions are same. So therefore I can put plus En1 into delta H by 2. Okay. So that is equal to 0. Now when you look at here, this plus En1 minus En1 cancelled, plus En2 minus En2 can cancel. So ET1 I can, ET1 minus ET2 into delta W, right, into delta W, that is equal to 0. So therefore it indicates that ET1 is equal to ET2. So this is my first boundary condition. This shows that this electrical field, this shows that electric field, the electric field in that is the electric field in tangential, right, in tangential component, electric field in tangential component is, tangential component is said to be, continuous, is said to be continuous, right. if this is continuous, right, continuous. So from this also we can say that what is the relationship with it? Electric flux density. So electric flux density is said to be, right, electric flux density, I can say that this is that is your D is equal to epsilon R into E, right. Generally we will put it as what is the flux density? Flux density D is equal to epsilon naught epsilon R into electric field. Now I want to find out ET1. ET1 means dt1, right. So therefore this I need to put it as dt1 divided by epsilon naught epsilon r1. Similarly, right, that is equal to, since I put it as et1 is equal to this, I am putting equal, right. So this side I will be having dt2 divided by epsilon r epsilon r2. So epsilon naught epsilon r will cancel out. So what is my dt1? So this indicates that dt1, right, dt1 is equal to epsilon r1 divided by epsilon r2 into dd2. So that means this is my second equation, right. This is my first equation. This is my second equation. So this show what does it shows? So though the electrical field in tangential component is continuous, but the electric flux in tangential is discontinuous because it is not equal, right. It is not equal. It depends on the parameter of epsilon r1 and epsilon r2. So the electric flux, the electric flux, so the electric flux in the tangential component or tangential component of electric flux, tangential component is said to be, right, they said to be discontinuous, is said to be discontinuous. Okay, this is my first boundary conditions, right. First boundary conditions what we have done is for tangential component we have analyzed, right. Similarly we need to do for the normal component, right. For tangential component the conclusion is the tangential, right, et1 is equal to et2. Electric field tangential component, if it remains the same or continuous, definitely the tangential component of the flux may not, electrical flux may not be same. So therefore we are telling that is said to be discontinuous, right. Next we will see, right, this is the first boundary condition. What is the second boundary condition is for the normal component, right. Again I'll take the same surface, right, same surface. So same surface with two different media, right. Different media, I told you this is permittivity is epsilon r1, permittivity is epsilon r2. Here what I am going to talk about is electric flux density, right. What is my electric flux density? Similar to electric field intensity, now I need to put it as d vector, right. So earlier we discussed, no, that is d component, right. D vector will also contain dt, right, that is a tangential plus normal component, right. Dt and dn, that is t means tangential, n means normal. So I'll be drawing the vector that, so this tangential component, right, this is my tangential, this is dt vector, right, dt vector, and this is dt2, right, this is dn2, right. This vector is this is your d vector, right, this is your d vector. Similarly in medium 1 this becomes, right, this becomes your this is d2, right, this is d2, this is your d1, right. There we have analyzed e1 and e2, here we are analyzing d1 and d2. So this is my d1 vector. So this is your tangential, right, that is this I can put d1, this is tangential t1, and this is your normal vector dt1, this is dn1, this is dt2 dn2, this is dt1 dn1, right. So therefore from this what you can we need to find out some boundary conditions for this electric flux density. For this what we need to do is we need to analyze for the closed surface. See, for example, right, in this closed surface what you need to do is, right, suppose if assuming that I have a in a particular electric field, right. So this is a surface, right, this is a surface. in which I am doing some surface analysis, right? So I have a cube like this, right? This is my surface I have taken into account, right? Therefore, right, when this cube, if you talk about, it will contain top, right? Top, bottom, this side 1, side 2, front, back. So if you look at front and back, these are all equal and opposite. And that here what you need to do is, this also can be, I can draw it as a cylindrical surface, right? This is a surface where, right, this is a surface where this top component is D, this is N1, and this is my Dn2. So what is this law says that, right? This is your from the Gauss law, right? From the Gauss law, I can say that what is the integration of d vector dot ds, right? That is equal to, so when you say this a cube, right? This is a small surface I am talking about, right? When I am finding out the what is the total flux inside this, that means that is depends upon the Q, right? Total charge enclosed in that cube, right? So so here we need to find out, right? How many surface, right? Either I can do is a which a whole surface of so this cube will contain 6 surfaces, or when you say that it is a kind of this cylindrical side, I can say top and bottom, right? So I can say the rest of the things is symmetrical, right? Since because of the symmetrical, being it's a closed surface, it is said to be symmetrical, and hence this component will get cancelled out. So what I can put it here is, so this becomes, right, integration of, because top and bottom, this I can say that top, right, top into d dot ds plus integration of d vector into ds bottom, and then all sides. So integration of this, simply I'll put it as, right, simply I'll put it as all sides, right? All sides are equal, right? Equal and opposite. So therefore it get cancelled out. So I can put it as 0, right? That is equal to Q, right? Now what I can substitute here is, what is the normal component in the this side? This is my dn1, right? What is the component here? This is dn2, right? dn2. So this is my normal, right? This is a normal vector. So I can put it as dn1, right? dn1, this is dn1 into delta s, right? This is my surface, right? This surface is, I can say that this is delta s, right? This is dn1 into delta s. What is this surface? This surface is, this normal vector is opposite. So therefore I can put minus dn2 into delta s, that is equal to charge, right? So therefore what I can do, I can take delta s as common, dn1 minus dn2 into delta s, right? That is equal to charge Q. See, generally we can say that charge per unit area or surface area, right? Surface area can be denoted as that is your surface charge density, that is equal to rho s, right? Rho s. So you can say that when you put delta s here, this becomes dn1 minus dn2 equal to Q by delta s, that is equal to rho s, right? So this shows that, so from this boundary condition, we can say whenever, right, whenever when the surface when the surface charge, here this condition we need to make an assumption, if the surface charge, right, if the surface charge is 0, if the surface charge is 0, then we can say that dn1, right, normal vector dn1 is equal to dn2. This is the third boundary condition, right? This is the third. First, already in previous tangential we have derived two conditions, and that is, those two are the for tangential component. For normal component, what we have discussed is, this is dn1 is equal to dn2. So therefore the normal component, right, the normal component of electric flux density, right, the normal component of electric flux density is said to be continuous, is said to be continuous, is said to be continuous. So from this, again, as we know, what is my d vector? D vector is epsilon naught epsilon r into E vector. Now what I need to do is, I need to substitute what is dn1. From this I can find out how does the normal component of electric vector behaves, right? That is that behavior I can analyze. So what I need to do is I need to substitute. What is dn1? dn1 is equal to epsilon naught epsilon r1 into en1, right? Therefore, so I can substitute epsilon naught epsilon epsilon r1 into e1, right? en1, epsilon naught epsilon r1 into en1 that is equal to epsilon naught epsilon r2 into en2. Okay, so this epsilon naught epsilon get cancelled out. What is my en1 component? En1 component is equal to epsilon r1 by epsilon r2 into en2. Now this is my fourth condition, right? This is my fourth equation. This shows that, right? So the previous equation shows that the normal component of the flux density remains the same. If the normal component of the flux density remains the same, the normal component of the field intensity may not be same. So the normal component, so this shows that the normal component, right? Normal component of field intensity, that is electric field, right? Normal component of the electric field is said to be discontinuous, This is the fourth conditions, right? So from this you can say that, right, that if the the four boundary conditions is used to analyze, right, how does the field, right, electric field, when the medium is getting changed, how the electric field vector, not only the tangential vector, that also the normal vector, right, not only for electrical field but also for the electric flux density, right, both. So concluding this, what you need to follow is, there are two law we are following. One thing is for the one thing what we have taken into account is, one thing is E into dl, right? So E into dl vector is equal to 0. This, in this case, what we have taken is, we have taken the closed path for analysis, right? From this we have derived two conditions, right? Two conditions we have derived. What are the two conditions? E T1 is equal to E T2. Then from this we have concluded that dt1, right? So this is dt1 is equal to epsilon r1 by epsilon r2 into dt2, right? This is where we have discussed, right? These are the two conditions we have finalized, right? That is your tangential component, right? And similarly, right, the second law what we have taken is, this is according to Coulomb's law, this is according to Gauss law, right? That is d vector into ds, that is equal to, right, equal to q. This, for this you need to take closed surface, right? So there it is a closed path, here it is a closed surface. This closed surface indicate that we have concluded this. Finally we have concluded the two conditions, right? What are the two conditions? This, according to, this is for the flux density. So the flux density dn1 is equal to dn2. From this we find out that en1, see, when you are talking about E tangential, D tangential. Similarly, D normal. What about E normal? So where the E normal vector, this, all this is are vectors, right? Et1, et2, dt2, dt1 vector, right? Similarly, dn1 is equal to n2. En1 vector is equal to epsilon r1 by epsilon r2 into en2 vector, right? This is the two conditions we have, boundary conditions we have derived. These are the two boundary conditions will help you to calculate when there is an electric field, when it get interfaces, right? When it crosses the medium, any kind of medium, how does the behavior of the electric field is getting changed in the other boundary, we can able to analyze. So the rest of the interfaces we will go through in the next class. Thank you.